to talk about some stuff from chapter one. Not all of it today, but a bit, and then we'll do the quiz. Um, the idea of chapter one is kind of setting the stage for what happens mathematically versus what happens computationally. So when we think about numbers, the first kind of thing that we think about would be a one-dimensional situation. So when we think of numbers, there's one dimension involved. What do we think of if we think about those numbers geometrically? We tend to think maybe just in terms of left and right, right? Maybe make a number line and think about the numbers in that way. Maybe we just think about something being bigger than something else, or being equal to something else, or something being smaller than something else. So one dimension, we have an idea. We're usually not going to draw the arrows at the end of things because we think it keeps going. But what we have graphics-wise, we will have limitations. We will stop somewhere, right? We have our window, or we have our world, or whatever we have some finite distance that's involved. But as far as mathematically, we think of this as being infinite. We also think of there not being any gaps between things. If you draw a number line like that, we think of there not being any gaps. But with a number line, what do we tend to do? We put some kind of starting point that maybe we call a 0 point. Now, where can the 0 point be? Yeah, the 0 point can be, we can choose where the 0 point is, right? We say, okay, here's our starting point. It can be relative to some physical situation that we're going to start at ground level and measure how far we've gone up the side of a building or something, and that be our distances that we're including. What would a negative number mean in that context? If we're talking about a building height. Yeah, he's going in a basement or going below ground level, right? So we could have positive or negative numbers in the beginning of numbers. People were counting physical things. So you're counting objects of some type. Well, eventually what might happen? You might realize that we have an inventory of whatever product, let's say, that we've made. And now we have orders for some that we don't have made yet. So now we have on supply, on hand, a negative number of things. So negative numbers are developed over time in this kind of idea of maybe owing something or being under stock. 0 comes along after the other numbers, right? After positive numbers, 0 comes along in the sense of I'm out of whatever. Okay, but what happens with these values? With numbers, we have a distinction between what are discrete and what are continuous. Discrete means that each thing is separate and we can look at each thing individually, maybe count each thing. There's not always, there's some issues we'll talk about in future with that. But discrete are things that are individual, they're separate. Continuous, no spaces between things. So if you think about discrete kinds of things are these integers that we were talking about. How many clay pots do we have? Right? One clay pot doesn't blend into the next clay pot. They're separate individual things. So discrete versus continuous, what do we tend to think of? We tend to think of, when we look around, we tend to think that things are continuous and everything kind of smoothly transitions. Physicists probably disagree. That the universe is actually discrete. Everything is discrete. Everything is its own separate portion. There's also the idea of finite versus infinite. how many things are there in the universe? Well, we probably live in a discrete and finite universe. A very big finite, but still finite. But what happens? What kinds of mathematics do we tend to use? Uh, Physicists tend to use calculus-related things and so on. They tend to use continuous mathematics that involves concepts of infinity. Why do that? If the world is really discrete and finite, why use these other methods? Well, often these other methods are easier to do certain calculations, and they give good answers. So it's easier and good answers, so let's go ahead and use those approaches. Sometimes that doesn't work out. Sometimes we do have to focus on the discrete and on the finite. And for our purposes, doing graphics kinds of things, even if we want something to mimic what would happen in a continuous and infinite world, we are forced to use discrete and finite techniques. What happens if we're drawing something on the screen? We're talking about pixels. Those are individual points. Are there an unlimited number of pixels? No, we can have a big number, but there's still a finite number, right? So they're individual things, it's discrete, and it's finite. Now, can you have discrete and infinite? Sure. Can you have continuous and finite? We can have all kinds of things. I guess we can mix and match. But the idea is that we are often pretending that things are continuous or pretending that things are infinite when they're not either of those things in our context. So there's a lot going on with one-dimensional stuff, with one-dimensional mathematics. We run into issues of like, how big are the numbers? How big can the numbers get that we're dealing with in our computer? What happens? How many numbers can we store? So how big can they be and how many can we store? What happens when we're trying to store a number that we can't store exactly? Then we get floating point errors and other things, and we'll see some of that. For our course, though, mostly we get to avoid all of the difficult aspects of one-dimensional mathematics. We just get to kind of, our numbers aren't so big and there aren't so many of them that we really have to get into the bad parts. But we will sometimes, and we'll talk about it as they come up. Mostly we get to just kind of continue on thinking about numbers the way we have thought about without any really weird, scary things happening. But sometimes those things do happen. And as we go forward in the program, there will be times in later courses where that will be much more relevant, and we will have to think about the distinctions, what's happening here and what's going on, and what does that mean for us. So as far as graphics is concerned, the topic, we are concerned with, on one hand, getting things, well, mostly we're concerned with getting things to look right. So the author of the text mentions the first law of computer graphics. If it looks right, then it is right. Sort of, right? Sort of. Is more so a different version of that. If it looks wrong, then it is wrong. Even if the mathematical details are correct, if it looks wrong, that's bad, right? So as far as presentation kinds of things go, we do care about how things look. Now, what do we want to do? We want to make it look as right as possible, and doing so in the best possible way. So there are sometimes best or better possible ways of doing things. But if things look wrong, then it's definitely, it doesn't matter how much work we put into it and how great the algorithm is, if it doesn't give us results that look right, then that doesn't satisfy anyone who's using our tool or looking at graphics that we've created. Anyway, so the author mentions that quite often through the text. Does it look right? Right, just keep thinking, does it look right? And often, the nice thing is, when we do the calculations in the correct way, then it does look right. All right, so there's an awful lot going on in 1D, and we're going to run into some of those problems, and as we run into those, we'll come back to them and think about them. 2 dimensions. By the way, I drew that line left and right, and then immediately started talking about the height of a building, which means we could have also have drawn that number line like this, or we could have drawn that number line like this. All right, we can draw a number line in any direction that we want, and we can then arbitrarily choose where the 0 is relative to whatever we want, right, for our benefit. If we're not going to have to deal with negative numbers at all, we can put the 0 all the way on one side. Even though there could be negative numbers, you don't have to think about them, so you don't worry about that. In 2D maths, what do we have? We tend to think of, geometrically at least, we tend to think in terms of 2 number lines crossing at right angles. That's the geometric approach. And we often do it like this, with a positive x and a positive y being a horizontal and a vertical. There are other ways to describe location in that kind of way. One way thinks of a starting point and then concentric circles around it. And when you want to describe some location, you describe how far away you are from the center, so you describe which circle you're on, and then you describe some angle. You think of an angle from here, and you think of an angle around, and often this is drawn still like this. So you think of how far away you are and then which angle you're at, and that will determine the point you're talking about. So if I want to talk about this point right here, I say, well, I'm this far away at this angle. And so this is a rectangular coordinate system. And this is often called a polar coordinate system, right? So 2 different kinds of coordinate systems, and there's others that we could have as well. But what do both of these do? Both of these have some starting point that we determine. We say, okay, here's our starting point. And then we determine relative positions, or positions relative to that starting point. Now, what happens if you use different, say, a different scale? If you are measuring these distances over here in millimeters, 1 millimeter, 2 millimeters, and so on, we get very different locations than if you measure those in miles or kilometers or light years. But they're still relative to other things. We would still know where things are, right? You give a distance. Well, you give a distance and an angle over here. We'll talk about that some more later. And over here, what do you give? You just give an x value and a corresponding y value. The rectangular system is also often called a Cartesian coordinate system, named after Descartes. And the idea is he's given credit, René Descartes is given credit for being the first to kind of formalize this. I don't know that he actually was the first. Lots of people were thinking about it at the same time. But he's given credit for thinking of this way of combining geometry and this algebraic approach of writing down values.
So why does Python use a rectangular like 2D, but the y values are the opposite?
Oh, so we'll talk about why Pygame does what it does in the particular direction in a bit. And so the idea is that since we can be arbitrary about where the center is, we might be able to have different choices about what's happening otherwise. And we'll talk about some of why that happens and what goes on. So this is the normal mathematical way, the typical way. This is a typical approach that you would see in a trig course or something. I don't know how true the story is. I was taught this as an undergraduate in a history of maths course, and we didn't have any actual references to go back to for this particular topic. It was just one of those kind of asides. And it said that Descartes lived in the early 1600s, and he I don't remember exactly the years, but he and a lot of other people were thinking about this connection between algebra and geometry, because what happens often? Often we have a geometry problem that would be helpful if we could use some algebraic equations to apply to it. or we have some algebraic situation, and it would be nice if we could draw pictures. And until that point, there was no really clear way to make these connections. Lots of ideas, lots of bits and pieces, but an awful lot of mathematics that we are used to just thinking about as, oh, it's always been that way. Some of those things are much, much newer. Now, of course, the 1600s were a long time ago, but not the 2,500 years ago that people were doing geometry in ancient Greece. The symbols that we use are much more recent. A lot of things are from, a lot of things that we learn in elementary school are actually from the 20th century. It just doesn't, it seems like it's been always that way, but it hasn't always been that way. So what happened, the story that I was told with Descartes was that he's working on this idea, had been thinking about it a lot, and that he was laying in bed one day, and the story was that he spent a lot of time in bed, and usually not alone, but I don't know how true that is, and that he was thinking about this idea and thought about, we looked at it at a ceiling, it was a tiled ceiling, and there was a spider walking across the ceiling. And it just hit him that, if I measure from the corner, I can say this many tiles over and this many tiles out into the room, and you get this exact idea. I don't know how true it is, but it is representative, right? It does describe the idea of how far over, left, right, and up, down am I from a particular starting point. And so with positive and negative values, we can talk about in any direction from there. And so we talk about things like a point, right? We have some point here. Let's say, maybe we have that point 2, 3. What does that mean? We've gone 2 in the x direction and 3 in the y direction, and we have that ordered pair that describes what's happening, where we are located. Now, we often are thinking in terms of integer values on this and kind of like a grid line, but this ordered pair idea works in between the grids as well. For graphics purposes, what will we have? We will be going maybe from pixel to pixel, and there is no in between, right? It's a discrete world. But there are also continuous things that we can think about. So what do we do if we run into a situation that needs something in between? Well, we can't do in between, say with Pygame. We have to go one way or the other, right, to make things work. All right, so what happens here? We have this 2D idea, and we've said that our first idea is to put x and y like this, but we also often are thinking in terms of like directions. If we were thinking in terms of direction, we put plus x, this then means negative x plus y and negative y. What if we were putting direction on here? What would we probably do?
North, south, east, west.
All right, we'd probably do north and south and then east and west like that. Because that's a typical way that we're used to seeing these things labeled. There is a map from somewhere, it's best dated in 1350s to the 1360s that it was made, a map of England, and it has cities and riverways and different major roadways laid out, has like pilgrim paths to various cathedrals and so on are all on this map. They dated this map by the names of some of the cities. There's one city whose name changed at a certain point, so it was, it has the old name, so that the map was made before that name change. And then there's another city that's drawn on the map with city walls around it, and they know what year those city walls were built. So it was after this date and before that date when this map was made. This map is called the Gough map. Sometimes it's called the Bodleian map. Because that's where it is stored now. But the Gough map has England, and east is up, and north is that way. Well, they drew east up because Jerusalem is to the east. And that was really important in the 1360s or 1350s. Which direction is Jerusalem? And so the pointing toward Jerusalem was east, was up. So when you look at the map, what do we do if we look at this map? We tend to turn our head or turn the map, right? If you turn the map, what happens? It looks like this now. If you turn your head, it looks like that now. So, so there was a different reason for east being up, but that was, it doesn't change anything from what we're used to now. We can just tilt our head and make things work. All right, so if we look at this labeling, once you choose where plus x is, that tells you where plus y, or excuse me, that tells you where minus x is, right? They're on the other opposite ends of the same line. We can't have something like plus x here and plus y there, right? This is the x line, this is the y line. And this is our typical way now of doing this. But what if we adjusted it like that? What have we done if we change plus x to point up and plus y to point to the left? Now negative x is down here and negative y is over there. This is a different coordinate system, right? But is it really different? It's the same idea as drawing the map and turn our head, right? If we turn our head, this is exactly the same as that. Or if we just turn this back to the right, it's exactly the same. All right, so this is two different ways that we could label the system, but it's not really different. So these two coordinate systems, it would look different if I said, go over 1 and we can't say go over 1 and up 2 anymore, right? It's go 1 in the x direction and 2 in the positive y direction. But what is it relative to where we are? Relative to where we are, looking at it from the right direction, tilt our head the right way or rotate things the right way. It's exactly the same situation. So if we just focus on where we are in terms of the positive x and the positive y, we're fine. If we get too worried about its orientation on a piece of paper that we're holding, then it's a problem. But what happens if you had this map and you had this map? If you're used to the one on the left, you just tilt your head if you're given the one on the right. If you're used to the one on the right, what do you do if you're given the one on the left? Yeah, you flip it just right? You flip it around. Maybe you have to look at it from the other side, but you flip it. You write it on a clear acrylic board with a marker, and you go to the other side, or you flip it around, and you can look at it from the other side, in that way. And you can make it work. It's no different from one to the other. All right. So how many different ways are there to create How many 2D systems are possible? We have 2 of them so far. And they're not different, right? They're kind of cosmetic differences, but underneath it, they're the same. All right, well, let's see what happens. How many choices do we have for where plus x goes? We have 4 choices of where to put plus x. We've looked at 2 of them so far. So we could put plus x over here or down here as well. But then once we put plus x in, how many choices are there for where we put plus y? 2 choices, right? So we have 4 choices to place plus x, and then 2 choices to place plus y. So how many choices in all? Well, any one of those 4 choices for x can lead to 2 choices for y. So what do we have? We have 4 times 2, 8 different ways to do this, right? 8 different coordinate systems that we could create. We have 2 of them here. Let's see if we can draw, all 8 of these. All right, so let's come back to here. What could we do? If I put plus x here, what could I have done instead? I could have made plus y down there instead of up top. Is that different than this? What could you do? Again, draw this one on an acrylic board with markers and just flip it over. Right? Look at it upside down and backward. And what happens? Plus x is still to the right, and plus y is back to pointing to the top. So, yeah, it looks a little different, but is it really different? No. Is that a familiar organization? Yeah, this is Pygame, right? Pygame says there's the upper left-hand corner, plus x this way, plus y this way. So it's not any different than what we're used to. There's a different reason that they do this as well, which we'll look at in a few minutes. But it doesn't matter. It doesn't change anything. All it changes is how we think about particular situations right then. So we have to know which of these 8 we're looking at. But so far, these 3 are all the same. So we know how to get back and forth between these 2. You have to tilt your head. And here you have to flip it over. How can you get between these 2? Probably a combination. Flip it over and tilt your head, right? All right, so what happens? We can get back and forth between these, back and forth between these. So all of them are the same. There are 5 more options, though. So let's see, what do we have? Let's take a look at this one. If we put plus x there, and then put plus y over there, can we get back to here? What do we have to do? If we tilt our head, which way are you going to tilt your head? We tilt our head to the right. So now we have plus y up, but plus x is in the wrong direction. So then we flip it, right? Tilt your head and flip. And you can get from here back to here. So then you could also do the same thing on any of these. What would you do for this one? Just flip. And what about this one? Just tilt your head, right? You just tilt your head, plus x up, plus y to the right. These 2 are tilting your head. This is a flip. This is both. All right, so we have 4 of them taken care of. There are 4 more. So what have we not looked at? Let's see. We have x at the top. Both of these have x at the right, plus x at the right. So we need plus x on the left. And we need plus x on the bottom. And there will be 4 of those total as well. Where can plus y go? Plus y can go to the top or to the bottom. And here, left or right. Now, which of these are different? What do we do to get from here back to here? Yeah, just flip it. Or again, go behind it, right? Look at it from the other side. From the other side, plus x would be to your right, and plus y is up. So those are still the same. What about this one? All right, that's again involving going to the other side and a flip, right? So go behind it and flip it maybe. All right, so that's another approach, right? Not going behind, but just completely turn ourselves and look at it from that way, right? So 180-degree rotation is another way instead of the flipping and so on. And so what happens? What do you think about these? This one, to get to here, what do we do? Tilt your head to the right, or turn it to the left one 90-degree notch. Here, again, maybe turning and flipping and so on, right? So what happens? There are 8 ways to do this, and all of them are exactly the same, right? Particular situations, and if we rely too much on, oh, go to the right. No, it's not go to the right, it's go positive in this, with this axis, or go positive with that axis, or negative in that axis. And so these 8 different systems are not really different systems, just different ways to write it down, but they're you can easily transition between one or the other, just with enough rotations or flipping or looking at it from the other perspective or something, right? All right, so 2-dimensional coordinate systems, it all comes down to really this one idea. So maths folks have settled on that one. Pygame settled on that one. Different systems will settle on different ones for different reasons, and we'll talk about what some of those reasons are. All right, so what happens then if we go to 3 dimensions? In 3 dimensions, we tend to, again, still think of a horizontal and a vertical. And then another dimension that either, we tend to draw it like this, that either goes into the board or a horizontal and vertical, and then something coming out of the board. And that's the way they tend to get drawn. Now, that's a 2-dimensional picture that's trying to describe a 3-dimensional idea. And so it doesn't work very well always. It's also very difficult sometimes to draw things that look 3D on 2-dimensional board. But what's the idea? There is some sense of left, right, up, down, forward, and backward. But all of those concepts are actually related to something about us relative to something else. Right? So it's really difficult to talk about left and right or forward and backward if you don't have something to refer to. But if you think about here for us, what could we think about in terms of 3 dimensions? We could think about the directions. North is that way. West. So we could think in that way for 2 things. I'm pointing this much north and this much west, or this much south and this much east, or whatever. What could we use for a 3rd dimension in that approach? Yeah, we could use up and down, and we think of down because there's gravity and so on, right? We know which direction is down because of that. So we could have an up and we could have a 3 values that are given in terms of some starting point. How far east-west did we go? How far north-south? And then how far up or down have we gone? Other approaches that correspond back to the polar coordinate idea, instead of it being circles, we think of a sphere. So you could think of the planet as roughly being a sphere. And we could give 2 coordinates that are in terms of like longitude, latitude. And then what could the 3rd coordinate be? Well, so a 3rd coordinate might be like a distance above sea level, which would really be measuring a distance from the center. Right, so I've measured this far out. Now I'm this far around this direction, and I'm this far around in this direction. And so there's lots of different ways, again, to describe 3-dimensional things. But usually with 3D, at least in a rectangular setup, we have the same idea of an X and a Y and this Z. So left, right, up, down, forward, and backward, whatever context that might mean. All right? So let's think about how many different 3D systems there are. let's think about how many choices do we have for plus x? Let's see, we're thinking of left or right. We're thinking up, down, and then we're thinking of forward or backward. So there are 6 choices. Any one of those could be the plus x direction. So plus x, there are 6 possibilities. Once we make that choice, how many choices are there for plus y? There are 4 choices for where plus y could be. And then what about the third component? There are 2 more for that, right? So what happens if we think about this kind of picture? Now we have all of these, but we have more than these just for x and y, because we also could have the positive x and the positive y kind of pointing toward us or away from us. So in all, how many different rectangular coordinate systems? 48. A big jump from the 8 in 2 dimensions. All right, now let's think about these. What do we have? We have some kind of idea here that we can think of using our hands to kind of keep track of what's what. So let's point our thumb, let's say, in the way we typically would do in an XY drawn like that. Let's point our thumb in the positive x direction. So that's going to be that way. Let's use our left hand. Put our thumb in the positive x direction. Put your first finger in the positive y direction. And now put out your middle finger. And that would be pointing in the positive z, right? Pointing that direction. So that would correspond to this base with x and y, and that third component pointing away from us into the board. Now, where do we want that third component to point if we are playing a video game? A first-person game, let's say. Forward probably would be pointing away from us into the screen. So that could make sense. If we had x and y, then if that direction could be pointing into the screen. All right, but that's not the only way that we could list this, right? So let's try it in a different way. What happens if we had what if we had plus x pointing in to the screen, and we had plus y over here? Can we change our hand to make that work? Well, that would be plus x pointing into the screen, and plus y pointing to the right. And where's our middle finger pointing? It is pointing up. And so that would be the same thing as well, right? So this and this are the same, just rotated around. Instead of pointing that direction, we've rotated around to look like that. So what does that mean about some of these 48? At least some of these 48 are the same. Are they all the same? That's our question now. All right, now we said that we could also have, instead of, we still have the x and the y pointing like that, but now instead of the third component pointing into the board, it could be pointing out of the board. That's the way, again, that mathematicians and physicists tend to think about it, because they're thinking about there's like a ground level and things are coming up from there. Right? You draw something. If you think about, say, drawing, we were talking about floor plans of this room sometime before today. And when you think of the floor plans, what do? You look at the floor plans and you kind of imagine that if you laid them down, that the building would be above there. And so it kind of makes sense for the third component to be coming out toward you. All right, so let's take our fingers that we have, our left hand that we have here, and let's make it match this. All right, if we make the x and the y match, what happens? That third component points the wrong way, doesn't it? No matter how hard we try to make, we can make two of the fingers match. What if we make these two match? The y and then x is wrong. What if we make these two match? Then y is wrong. So what happens? This is different than that. Let's use our right hand instead. X, y. That works, doesn't it? So it turns out that these 48 are not all the same. Take your right hand and your left hand now, holding them in that way. Now let's move your right hand and your left hand around so that they are exactly, everything matches up. All the fingers match up exactly. What happens? You can get two of them to match, but if two of them match, then the third ones are pointing in the opposite direction. You can get any two to match, but then the third finger is pointing the wrong way. So of these 48, we get two categories. We get what's called a left-handed coordinate system, that you can mimic with your left hand, and we get a right-handed system that you can mimic with your right hand. So the 48 actually are two different systems. And when you have two different systems, then it does matter which one you've chosen. On the x and y coordinate system, just a two-dimensional thing, it doesn't matter which one you choose. You just tilt your head the right way, or you look at it just the right way, and everything's exactly the same. What happens here? There are differences. Now, is one more correct than the other? No. You just have to know which one you're talking about. So it turns out certain calculations will be different if you're in a left-handed system versus a right-handed system. And what kind of differences are we talking about? Usually we're talking about a sign. Something needs to be negative somewhere. Right? If you think about the two left-handed and right-handed, usually it's just take that third component if things don't look right and flip it, make it negative, and then things will look right. So going back and forth, and that's usually the situation in terms of left-handed versus right-handed. Well, why would there be a difference? Why would you specify left-handed versus right-handed? It depends on what kinds of things you tend to be doing. Right? What makes sense in your context? It makes sense if you are building a building. If we're used to thinking of x in the horizontal that way and y in the vertical this way, that the third dimension would be toward us, because that really corresponds to going up in that case. So even though up the screen might be up, also this way might be up. So if you've already settled x and y in that way, then up might make sense this way. That would be a right-handed coordinate system. But if you've already settled x and y in this way, then up would be into the screen, and that would be a left-handed system. So it depends on what you're trying to do. Now, what do we have in Pygame? In Pygame, we have x that way, positive x, and positive y that way. Now, Pygame's not three-dimensional, but let's pretend for a second that it was, and we wanted our positive in that direction to be into the screen because it's going to be a first-person thing. Is that left-handed or right-handed? So if we do this left-handed, we put x and y, and which direction does the third component point? Would point toward us. So it's not left-handed because it's pointing in the wrong direction. Let's make it right-handed. X and y, and now where does the other finger point? Into the screen. So if Pygame were going to have a third component, which it doesn't, but we can pretend like it does, but it doesn't, And if it pointed into the screen, that would actually be a right-handed system. Does that make sense? So Pygame designers wanted the upper left-hand corner to be a fixed point instead of saying the bottom left-hand corner. And they wanted a right-handed system. And so to get a right-handed system, I mean, maybe this might not have been their choice. It might not have been their reasoning for their choices. But let's say, right, they wanted the upper left-hand corner, which they did. And let's say they wanted a right-handed 3D representation. Then what happens? X and Y in that direction to make that work out. All right? And so of these 48 options that we have, really 2 of them are different, right? There are 24 of one kind, 24 of the other kind. And so what do? We have to know what kind of system we are in. We have to know whether we're in a right-handed or a left-handed system. Like I said, there are things that happen in different industries. Aerospace has a particular set of standards that they use that says this is where positive X is, this is where Y, and so on. If you think about what's happening with a plane that's flying, what do you have to think about with a plane? You think about how far, where is it pointing, say, toward the north, right? In this particular case, there's roughly north. So how far off away from north are you? That's one direction that they're concerned with. What else are they concerned with? They're concerned with pitch. Is it up or down or level? And then they're concerned with this direction. Right, so there are 3 different axes that they care about. They care about an axis that points to the north, and where are you relative to it? They care about an axis that is this way across the body of the plane. That's going to determine this direction. And then they care about an axis care about an axis that's down the middle of the plane. It's in terms of where you rolled this way, right? So we have an axis that's actually pointing this direction. How are you rotating around it? That's the first one, right? This way. And then we have, 3 axes in all. One that runs down the middle of the plane, that determines this. One that runs across the plane, which determines, when I say plane in that case, I meant like an airplane, right? Not, although it is still actually a 2-dimensional plane that you can think about. But this way, and then we have this axis that's determining, are we pointing north or which direction are we pointing? All right, so they have choices. They make their choices of what different ones and what the order of those mean and so on, right? Which is most important, but which one do we consider first? What is in the first slot? What is in the second slot? What is in the third slot? And it's the same thing that we're going to do, which is where at different points. All right. So we also then have this idea of, once we know location, we're talking about rotation. So we're talking about rotation kinds of things. And if you think about trig, in trig we tend to start with the starting point here, and then a positive rotation is that direction, is counterclockwise. Right? So it rotates that way. The way to figure out positive rotation is to, let's use our thumbs in a different way now. Let's point our thumb in the direction of the axis of the rotation. So if something is going to rotate this way, it's rotating about an axis that is perpendicular to both of those. Right? You imagine we have a merry-go-round. Which way, merry-go-round is spinning around. But what is it spinning around? It's spinning around a pole that's here. Right? So it's spinning. Here's the pole, and it's spinning around the pole like this. All right, so the axis of rotation is perpendicular to both of these. So if you point your thumb in the direction of the positive axis of rotation, then your fingers will curl in the positive rotation direction. So we think about our regular 2-dimensional thing with positive x in that direction and positive y in that direction. If positive, the third component, the z value, if it's this way, Put your fingers here. Put your thumb in that direction and curl. What kind of thing are we looking at here? If that's the positive direction, this is a right-handed system. Does that make sense? Now, what if this had been a left-handed system? Left-handed system, you put your thumb in the positive direction there, and your fingers curl in the positive direction. Still the same direction. So if that's positive x and that's positive y, then whether it's right-handed or left-handed, that is positive rotation. Does that make sense? So it depends on, so in that case, the two-dimensional thing doesn't really depend on the three-dimensional, which system you're using, but that is the reason that that is positive rotation. That's anti-clockwise, it's counterclockwise, right? But it's because of positive curling in the direction that your fingers would curl. Now, why is it that way? Well, that's a choice that was made at some point, right? What does it mean to be a positive rotation? Well, that makes sense. As we're representing this first in a physical kind of way, that makes sense if it's right-handed or left-handed. And so we're curling in this direction. Now, what happens in some other situation? Right? Again, you point your thumb in the direction of the rotation, or the axis of rotation, and then point your fingers where it starts and curl toward where it's going. If it curls that way, that's a positive rotation. If the rotation was actually going the other way, then that means that would have been a negative rotation from there. All right? Does that make sense? All right, so we will do a lot more with this, but this is the first part of Chapter 1. You want to read Chapter 1 for next time. And then as we go forward, we'll talk about chapters, and you'll want to keep tracking. This is reading the ones in the 3D maths, whatever, primer. All right.